March 15, 1945. A grey morning hung over the Mitsubishi Heavy Industries research facility in Nagoya, where Chief Engineer Takeshi Yamamoto stood before the most pristine Wright R3350 radial engine he had ever seen. The 18-cylinder power plant, still smelling faintly of aviation fuel and the peculiar sweetness of American lubricants, had been extracted from a B-29 superfortress that had made an emergency landing in a rice paddy near Shizuoka just 48 hours earlier. Yamamoto's hands trembled slightly as he ran his fingers along the engine's cowling, feeling the precision of its manufacture, the absolute perfection of its tolerances. Around him, 6 of Japan's finest aeronautical engineers waited in silence, each carrying the weight of an impossible assignment. The irony would have been almost comical if the stakes had not been so desperately high. These men, who had spent years designing engines that routinely failed after mere dozens of operational hours, believed they could unlock the secrets of American engineering superiority in just 2 days. They were convinced that there must be some trick, some hidden technique that explained why these massive engines could fly for hundreds of hours without failure, while their own creations burned out, seized up, and left Japanese pilots stranded over hostile waters. Before we dive into this story, make sure to subscribe to the channel and tell me in the comments where you're watching from. It really helps support the channel. What these engineers would discover in those 48 hours would shatter everything they believed about their own industrial capabilities and reveal a truth so profound that it would haunt them for the rest of their lives. This is not merely the story of an engine examination. It is the story of how a group of brilliant men came face to face with the limits of human ingenuity when confronted by the overwhelming power of industrial civilization. Takeshi Yamamoto had not slept in 36 hours when the telephone call came. At 53 years old, he was the most respected engine designer in Japan, a man who had dedicated his entire career to the pursuit of aeronautical excellence. His Kinsei radial engines powered many of the aircraft that defended Japanese airspace, and he had personally overseen the development of the Kasei engine series that equipped medium bombers across the Pacific. Yet standing in his office at 3 in the morning, listening to the urgent voice of a military liaison officer, he felt something he had not experienced since his earliest days as an engineering student: genuine fear. The captured B-29 had been a gift from the heavens, or perhaps, he would later reflect, a curse. The aircraft had suffered damage to its control surfaces during a mission over the Japanese mainland and had been forced to land when hydraulic failure made it impossible to maintain altitude. The crew had been captured, but more importantly, the aircraft itself remained largely intact. Within hours, military intelligence had ordered the most critical components transported to various research facilities across the country. The engines, those magnificent, mysterious engines that seemed to defy every principle of metallurgy and thermodynamics, had been sent to Yamamoto. He assembled his team with care. There was Hiroshi Nakamura, 31 years old, a metallurgist whose work on high-temperature alloys had shown genuine promise before the resource shortages had crippled his research. Kenji Watanabe, 45, was a precision machinist who had trained in Germany before the conflict and understood tolerances with an almost spiritual intuition. Yuki Tanaka, the youngest at 28, had specialized in fuel systems and carburation, bringing a fresh perspective that sometimes irritated his elders, but often proved invaluable. Masao Ishida handled ignition and electrical systems with a quiet competence that inspired confidence. Finally, there was Saburo Endo, 58 years old, a veteran engineer who had worked on aircraft engines since the 1920s and whose institutional memory stretched back to the earliest days of Japanese aviation. These 6 men gathered in the research facility at dawn on March 15th, knowing they had exactly 48 hours before the engine would be transferred to another facility for further study. 48 hours to unlock secrets that had taken American engineers decades to develop. 48 hours to find the weakness, the flaw, the Achilles heel that would allow Japanese industry to close the gap that was slowly strangling their nation. The first hour was spent simply looking, Yamamoto insisted on this, overruling the younger engineers who wanted to begin disassembly immediately. He understood that sometimes the most important information revealed itself to patient observation. They walked around the engine slowly, examining it from every angle, noting the placement of components, the routing of fuel lines, the configuration of the exhaust system. They photographed everything, made sketches, took measurements, and with each passing minute, the silence grew heavier. It was Nakamura who spoke first. "The surface finish," he said quietly, running his hand along the cylinder head. "Look at the surface finish." The others gathered around, and Yamamoto felt his stomach tighten. The machining was flawless. Not merely good, not merely excellent, but perfect in a way that seemed almost impossible. Every surface gleamed with a uniformity that spoke of tolerances measured in 10,000ths of an inch. In Japanese factories, such precision was achieved occasionally on individual components through the heroic efforts of master craftsmen working by hand. Here it was everywhere, on every single part, suggesting not individual genius but systematic, reproducible perfection. Watanabe produced his precision measuring instruments and began taking readings. His face grew progressively paler as he worked. "The tolerances," he murmured, almost to himself. "They are holding tolerances we cannot even measure reliably." He showed Yamamoto his findings. The clearances between moving parts were so precise, so consistent, that they approached the theoretical limits of what machine tools could achieve. And they were maintained across every single component, from the largest cylinder to the smallest valve spring. By the third hour, they had begun careful disassembly. Yamamoto had established strict protocols. Every component was to be photographed in place before removal, labeled, measured, and catalogued. Nothing was to be damaged or modified in any way that might obscure its original condition. They worked with surgical precision, and as each part came free, the magnitude of what they faced became clearer. The cylinder sleeves emerged first, and Tanaka actually gasped when he saw them. The nitride hardening was deeper and more uniform than anything Japanese metallurgy could produce. The honing marks on the cylinder walls were so fine, so precisely angled, that they created an optimal surface for oil retention while minimizing friction. When Nakamura tested the hardness of the material, he found it exceeded their best efforts by a significant margin. And yet the sleeves were not brittle. They had somehow achieved hardness without sacrificing toughness, a combination that Japanese engineers had been struggling to master for years. As the afternoon wore on, the discoveries accumulated like evidence in a trial where the verdict was already certain. The piston rings were made from an alloy they could not identify, maintaining their spring tension even after hundreds of hours of operation at temperatures that would have destroyed Japanese rings within 50 hours. The valve seats showed minimal wear despite operating in an environment of extreme heat and corrosive combustion gases. The supercharger impeller blades were forged from aluminum alloy with a strength-to-weight ratio that seemed to defy the known properties of the metal. But it was the small things that truly devastated them. Every single fastener, every bolt, every nut, every screw was perfectly formed, with threads that engaged smoothly and held their torque specifications exactly. In Japanese engines, fasteners were a constant source of problems. They stripped, they loosened, they failed. Engineers spent countless hours selecting and matching individual fasteners by hand, trying to find combinations that would hold together under the stresses of operation. Here, every fastener was interchangeable, identical, perfect. You could select any bolt at random and know it would perform exactly as specified. Ishida, working on the ignition system, discovered that the magnetos were shielded against interference in ways Japanese designers had not even considered. The wiring harnesses were made from materials that resisted heat, oil, and vibration with equal efficiency. The spark plugs were designed with electrode geometries that optimized combustion while minimizing wear. Every single component reflected not just clever design, but the ability to actually manufacture that design consistently, reliably, in enormous quantities. By midnight of the first day, the team had filled dozens of notebooks with observations, measurements, and sketches. They had taken over 300 photographs. They had identified no fewer than 47 significant technological advantages in materials, machining, and design, and they had found exactly 0 weaknesses. Yamamoto called a halt at 2 in the morning, ordering his team to rest for a few hours. But he could not sleep himself. He sat in his office staring at the pages of notes and felt a profound shift occurring in his understanding of the world. For years he had believed that Japanese engineering was approaching parity with the West, that their disadvantages were temporary and could be overcome through superior effort and dedication. Now he understood that he had been measuring with the wrong ruler entirely. It was not that American engineers were smarter. His own team included some of the finest minds in the country, men whose theoretical understanding of thermodynamics and aeronautics was genuinely world-class. The problem was that American industry could take a brilliant design and reproduce it perfectly, thousands of times, with every single unit matching the original specifications exactly. Japanese industry, starved of resources, dependent on hand craftsmanship to compensate for inadequate machine tools, simply could not do this. The gap was not in knowledge, but in capability, and capability could not be bridged by working harder or being more dedicated. The second day began with a deeper examination of the engine's internal components. They removed the crankshaft, and the discovery that awaited them was perhaps the most demoralizing of all. Japanese crankshafts were notorious for their problems. The stresses involved in converting reciprocating motion to rotary motion at high speeds were immense, and Japanese metallurgy had never quite solved the problem of creating shafts that were both strong enough to handle these stresses and smooth enough to avoid vibration-induced failures. Engine seizures due to crankshaft problems were common, and pilots had learned to treat their engines with extreme caution to avoid catastrophic failures. The American crankshaft was a masterpiece. The forging was flawless, with a grain structure that distributed stresses evenly throughout the metal. The journals were ground to a mirror finish that seemed impossible for a component of this size. The counterweights were positioned with a precision that resulted in perfect balance. Watanabe tested it repeatedly, unable to believe his instruments. When Nakamura analyzed a small sample of the metal, he found an alloy composition that Japanese steel mills could not reproduce. The Americans had somehow managed to add chromium, nickel, and molybdenum in proportions that created exactly the properties needed: strength, toughness, fatigue, resistance, and the ability to take a perfect surface finish. Endo, the veteran engineer, spoke for the first time in hours. "I have been designing engines for 33 years, he said quietly. "I have seen the best work that Japanese craftsmen can produce. I have seen German engines, British engines, engines from all over the world." He paused, his weathered hands resting on the crankshaft. "I have never seen anything like this. This is not just engineering. This is industrial power of a kind I did not know existed." The team continued their work, but a change had come over them. The frantic energy of discovery had been replaced by something more somber, more reflective. They were no longer searching for weaknesses to exploit. They were trying to understand a civilization. The fuel system revealed its own lessons. The carburetors were equipped with automatic mixture controls that continuously adjusted the fuel-air ratio based on altitude and temperature, a problem Japanese engineers had struggled with throughout the conflict. Their own aircraft required constant manual adjustment by pilots, who had to divide their attention between flying, situating themselves, and managing their engines. American pilots could simply fly, trusting their machines to optimize themselves. The fuel lines were made from synthetic rubber that resisted deterioration from aviation fuel, another material Japanese industry could not produce in quantity. The fuel pumps were designed with redundancy built in, so that a single failure would not doom the engine. Tanaka spent hours examining the supercharger system and emerged shaken. The impeller was a single piece of forged aluminum alloy, shaped with aerodynamic precision that maximized pressure ratio while minimizing the temperature rise that robbed engines of power. The bearings were lubricated through channels machined directly into the housing, ensuring cool oil reached the critical surfaces at all times. The entire assembly was balanced to tolerances that Japanese facilities could not even measure, let alone achieve. A supercharger that vibrated was a supercharger that would fail, and this one did not vibrate at all. By the afternoon of the second day, They had largely completed their examination. The engine lay disassembled across multiple workbenches, each component tagged and catalogued, each secret revealed. And the revelation was not what any of them had expected. There was no single trick, no hidden technique, no magic formula that explained American superiority. Instead, there were thousands of small advantages, each one building on the others, creating a whole that was far greater than the sum of its parts. Better steel allowed better machining. Better machining allowed tighter tolerances. Tighter tolerances allowed higher compression ratios. Higher compression ratios allowed more power from the same displacement. More power allowed heavier aircraft. Heavier aircraft could carry more fuel, more defensive armament, more bombs, and it all began with the quality of the steel, which depended on the quality of the ore, the efficiency of the smelters, the availability of alloying elements, the sophistication of the metallurgical testing. A chain of capabilities stretching back to mines and factories and research laboratories that Japanese industry simply could not match. Yamamoto assembled his team for a final meeting as the sun began to set on March 16th. They had perhaps 2 hours before military transport would arrive to take the engine to its next destination. He looked at the faces around him, tired, drawn, reflecting the weight of what they had learned. These were men who had dedicated their lives to engineering excellence, who had pushed Japanese industry to its limits and beyond. And now they understood, truly understood what those limits meant. He asked each man to share his conclusions, and what emerged was a portrait of industrial civilization so complete that it left no room for illusion. Nakamura explained that the Americans were not using secret alloys or mysterious processes. They were using standard materials, well documented in engineering handbooks, but they were producing those materials with a consistency and purity that Japanese steel mills could not approach. The difference was not knowledge, but capability. Hundreds of qualified metallurgists instead of dozens, thousands of calibrated testing instruments instead of hundreds, an industrial infrastructure that could maintain quality control across millions of tons of production. Watanabe described the machine tools that must exist in American factories, grinding machines capable of holding tolerances of 50 millionths of an inch, milling machines that could cut complex shapes in hardened steel without losing accuracy, measuring instruments that could detect variations invisible to the human eye. Japanese factories had some such tools, imported before the conflict or built by hand in small numbers. American factories must have them by the thousands, operated by workers trained to use them properly, maintained by technicians with the skills and parts to keep them running. Tanaka spoke about the fuel system design, which reflected not just clever engineering, but a culture of continuous improvement. Every component showed evidence of refinement, of lessons learned from testing and operational experience. The Americans were not just building engines, they were building systems to improve engines, collecting data from thousands of hours of flight time, analyzing failures, implementing solutions, and then testing again. It was engineering as a process, not just a product, and it required resources that Japanese industry did not possess. Ishida noted that the electrical system showed similar sophistication. The wiring was color-coded and labeled, making maintenance simple and reliable. The connectors were waterproof and vibration-resistant. The entire system was designed not just to work, but to be maintained by ordinary technicians under field conditions. Japanese engines required expert attention and specialized knowledge to keep running. American engines were designed to be maintained by anyone who could follow a technical manual. This meant that even if Japanese and American engines started with equal reliability, the American engines would stay reliable longer because they would actually receive proper maintenance. Endo, speaking last, placed the findings in historical context. He had watched Japanese aviation grow from its earliest beginnings, had seen engine technology progress from primitive copies of foreign designs to genuine indigenous achievements. He had believed, truly believed, that Japan was closing the gap, that dedication and sacrifice could overcome material disadvantage. Now he understood that the gap was not closing, but widening. Every month that passed, American factories were building more and better machine tools, training more skilled workers, producing more high-quality materials. Japanese industry, strangled by shortages, increasingly dependent on improvisation and hand labor to replace worn-out equipment, was falling further behind. The longer the conflict continued, the worse the disparity would become. Yamamoto listened to each man and felt the weight of responsibility pressing down on him. He would have to write a report. Military authorities would want to know what had been learned, what weaknesses had been discovered, what countermeasures could be developed, and he would have to tell them the truth, that there were no shortcuts, no tricks, no secret techniques that could close the gap. The only solution was to build the entire industrial infrastructure that made such engines possible. The steel mills, the machine tool factories, the chemical plants, the training programs, the research laboratories, and that would take decades, even in peacetime, even with unlimited resources. But he also felt something else, something he had not expected, a profound respect, even admiration, for what the Americans had achieved. This engine was not the product of genius alone. It was the product of a civilization, a whole society organized around the systematic creation of material abundance. Thousands of people had contributed to this single engine: miners, steelworkers, machinists, engineers, technicians, inspectors, each one doing their part with skill and dedication. It was a collective achievement of staggering scope, and it represented something genuinely new in human history. The ability to produce complex, sophisticated technology, not just in ones and twos, but in thousands, with each unit essentially identical to every other. The transport arrived at 7 in the evening, and the team carefully repacked the engine components for shipping. Yamamoto watched his engineers work and saw how they handled the American parts. Gently, almost reverently, as one might handle precious artifacts from an ancient civilization. In a sense, that was exactly what they were. Artifacts from a civilization that had mastered the creation of material wealth to a degree that Japan had not yet achieved. In the weeks that followed, Yamamoto wrote his report. He documented every finding in meticulous detail, filling hundreds of pages with measurements, analyses, and conclusions. He knew that most of it would be ignored or suppressed. Military authorities did not want to hear that the situation was hopeless, that no amount of effort could close the gap in time to affect the outcome of the conflict. But he wrote it anyway, for the record, for history, for the young engineers who would someday need to understand what had happened and why. He also wrote a personal addendum that he kept separate from the official report. In it, he reflected on the larger meaning of what he had witnessed. The engine, he wrote, was a symbol of something beyond mere technology. It represented a way of organizing human effort that was extraordinarily effective at creating material prosperity. The Americans had not achieved their industrial superiority through any special virtue or intelligence. They had achieved it through systems. Systems for extracting resources, systems for refining materials, systems for training workers, systems for controlling quality, systems for continuous improvement. These systems had taken generations to develop, and they could not be copied overnight. But they could be studied, they could be understood, and in time, given peace and resources and patience, they could be adopted. Japan's future, Yamamoto wrote, lay not in trying to beat the Americans at their own game, but in learning from them, in understanding the principles that made their industrial civilization so powerful, and in applying those principles to build a new kind of Japanese industry. The conflict would end, one way or another. What mattered was what came after. The engine itself continued its journey through the Japanese research establishment, examined by team after team of engineers who reached the same conclusions Yamamoto had reached. Some tried to implement improvements based on what they learned, but without the underlying industrial infrastructure, these efforts achieved little. You could not make better steel without better furnaces. You could not hold tighter tolerances without better machine tools. You could not maintain quality control without trained inspectors and calibrated instruments. Each problem led back to others, in an endless chain of dependencies that could not be broken without rebuilding the entire system. The members of Yamamoto's team returned to their regular duties, but they were changed by what they had experienced. Nakamura began keeping detailed notes on metallurgical processes, determined to preserve knowledge that might someday be useful for rebuilding Japanese industry. Watanabe started training young machinists in precision techniques, knowing that the skills would be needed when peace came. Tanaka threw himself into improving fuel system designs, achieving small gains that helped aircraft performance even if they could not close the overall gap. Each man contributed what he could, working within the constraints of a system that was slowly breaking down around them. Yamamoto himself continued designing engines until the end of the conflict, and then he did something that surprised everyone who knew him. He took a position with a civilian manufacturing company and spent the next 2 decades helping to build the industrial infrastructure that Japan had lacked. He worked on quality control systems, on machine tool development, on training programs for skilled workers. He never designed another aircraft engine, but he helped create the foundation that would eventually allow Japan to become an industrial power that could match and even exceed American manufacturing in certain fields. Years later, when he was an old man, Yamamoto was interviewed by a journalist who was writing about the history of Japanese aviation. The journalist asked him about the B-29 engine examination, which had become something of a legend among engineers. What had he really learned in those 48 hours? Yamamoto thought for a long moment before answering. "I learned," he said finally, "that there are no shortcuts. I learned that industrial civilization is not a single achievement but 1,000 achievements, each one depending on all the others. I learned that you cannot copy the products of such a civilization without first building the systems that create those products. And I learned that building those systems is the work of generations, not days or months or even years." He paused, looking out the window of his office at the city that had risen from the ashes, at the factories and laboratories and training centers that had been built in the decades since the conflict ended. "But I also learned something else," he continued. "I learned that it can be done. The Americans were not superhuman. They had simply been working on their systems longer than we had. Given time and peace and determination, we could build the same capabilities. And we did." The journalist asked one final question. Did he have any regrets about the examination, about what he had discovered and reported? Yamamoto shook his head slowly. "No regrets," he said. "Understanding the truth is always better than believing comfortable lies. That engine taught me the truth about industrial civilization, and that truth guided the rest of my life. How could I regret that?" The engine itself disappeared into the chaos of the conflict's final months and was never seen again. Perhaps it was melted down for scrap, or buried in rubble, or simply lost in the general destruction. But the knowledge it had imparted lived on in the minds of the men who had examined it, and through them it helped shape the future of Japanese industry. Today, Japan produces some of the finest precision machinery in the world. Its manufacturing processes are studied and copied by engineers from every country. The quality control systems that Yamamoto and his colleagues helped develop have become global standards. In a very real sense, the lessons of those 48 hours in March 1945 are still being applied, still bearing fruit, still demonstrating the power of understanding over illusion, and somewhere in the archives Yamamoto's report still exists. Hundreds of pages of careful documentation recording the moment when a group of brilliant engineers came face to face with the true meaning of industrial civilization. It stands as a testament to their integrity, their professionalism, and their willingness to see the truth even when that truth was painful. They could not change the outcome of the conflict they were living through, but they could learn from it, and in learning they helped create a better future. The 48 hours that Takeshi Yamamoto and his team spent with the Wright R3350 engine changed their lives and, in some small way, changed history. They went into that examination looking for weaknesses and found instead a mirror that showed them their own limitations. They emerged with knowledge that was useless for winning the conflict, but invaluable for building the peace that followed. They learned that true strength comes not from secret techniques, but from patient, systematic development of capabilities. And they learned that such development is possible for anyone willing to do the work. That is perhaps the most important lesson of all. The Americans who built that engine were not geniuses or wizards. They were ordinary people working within extraordinary systems. Those systems had taken a long time to build, but they were built by human beings, and they could be built again by other human beings in other places. The engine was proof that industrial civilization was achievable, that material abundance was not a fixed quantity, but could be created through organized effort. And that proof, that demonstration of what was possible, may have been the most valuable thing that engine ever produced. And that concludes our story. If you made it this far, please share your thoughts in the comments. What part of this historical account surprised you most? Don't forget to subscribe for more untold stories from World War II, and check out the video on screen for another incredible tale from history. Until next time.